Hey everyone, good evening and good morning to Jonas and Matthew. This is Adi, founder at Summer of Bitcoin, where we are helping university students learn about Bitcoin and hopefully contribute to the Bitcoin open source ecosystem. Today we have Matthew with us. Hey Matthew. Matthew
how are you?
is the lead developer at impervious.com. He has also implemented the JavaScript version of a Bitcoin full node, Bcoin. You guys should check that out for those of you who are JavaScript ninjas. And he has a lot to his name. You could check out Block Clock, which is another sort of a full node and a clock. And he did that way back in 2015, if I'm not wrong. He's been around since 2013, around the time when people were using Mt. Gox. That was an old exchange that got hacked. And there's a lot of history, nice history around it that you guys might want to check out when you're free. Anyway, with that, I'm going to hand it to Matthew, who's going to talk about a lot of interesting things, which is relevant for a technical audience such as you. Take it away, Matthew.
Thanks. Thanks everybody for attending. I just want to make clear that I was a contributor to Bcoin. I didn't invent that project, but I did work on it for several years. And for those of you who are JavaScript ninjas, like Adi said, it's an excellent project to check out and play with. It's a very useful library for creating Bitcoin transactions and other library functions. And you might find the code base, especially if you're more familiar with JavaScript, you might find the code base more legible than Bitcoin Core, which can get verbose and terse in some areas. But of course, it's not as secure or as well reviewed as Bitcoin Core. So that's Bcoin. As Adi said, my name is Matthew Zipkin. You've got my email here on the screen and my PGP public key. And I will explain what a public key is in a little bit for those of you who don't know. And I work for a company called impervious.com, not impervious.ai. That's an unfortunate name collision. We work on Bitcoin software and also on Handshake, which is another blockchain, a little bit like Bitcoin, but it does naming and stuff like DNS. So this talk is called A Deep Dive into Bitcoin Mechanics. And the way that this talk is designed is I'd like to explain some basic Bitcoin concepts to you using simple metaphors and some fun concepts. And the talk is designed for engineers and developers that are just getting into Bitcoin. So I'm going to use some technical terms, but they also might be, I'm also going to make up some terms just for the sake of getting these concepts across. And in some cases, some of these concepts might be old to you or too basic, but I think even in those cases, you may find that the way that I'm presenting these metaphors maybe will help you explain them to other people. So if you already kind of understand some of these things about Bitcoin, maybe this will help you think about it in a different way and help you explain Bitcoin to your friends or to other developers as you go through your career. So to first define Bitcoin, if someone asks you what is Bitcoin, usually what I'd like to do is redirect that question and say, what is email? You can think of email as three different things. It's a unit of correspondence, like, oh, I sent you an email, or I got 10 emails today. You can think of it as a computer program like Gmail or Outlook or Thunderbird or programs that do email. And finally, you can think of it as a network of computers running such a program and following a protocol. And that's important. Protocol is, a list of rules, and they define how these computer programs talk to each other in order to exchange these units of correspondence. So, email follows a protocol called SMTP. And one rule about the email protocol is that email messages have to have a from value and a to value. That's just an idea of a rule. And if you follow those rules, then programs like Outlook can send emails to Gmail and Thunderbird and like that, because they're all following the same protocol, but there could be multiple implementations. So bringing that back to Bitcoin, we can say that Bitcoin is a unit of monetary value, like that coffee costs 0.01 Bitcoin, or I get paid in Bitcoin. Bitcoin is also a computer program. I use Bitcoin Core for my full node and wallet. Bcoin is a Bitcoin full node written in JavaScript. And finally, Bitcoin is a network of computers running such programs that follow a protocol. And two examples I have here of rules in the Bitcoin protocol are that the Bitcoin protocol prevents a person from spending money they don't have, and the total supply of Bitcoin will never exceed 21 million BTC. So what is Bitcoin? It's these three things. It's a unit of value, it's a computer program, and it's a network of computers running that program following a protocol. Same way that email is a message, it's a computer program, and it's a network. So when you think about email, here I've got some characters I hope everybody recognizes: Homer, Bart, Lisa, and Nelson, and they are all running email programs on their computers, which allow them to send email correspondence to each other. And each of their computers has its own database, and they're able to send messages to each other by following a protocol. So email servers connect to other email servers, and they follow certain protocol rules to maintain a database of messages for the user. So Homer's database is different than Lisa's database, but they can still send emails to each other. We have these protocol rules that must be enforced, for the sake, Homer doesn't want to get an invalid message from anybody, so his computer program prevents those kind of messages from bothering him, So Bart sends an email to Homer, and it has a to and a from and a subject and a message, and Homer's computer welcomes that message and adds it to the database because it's a valid message. Meanwhile, Nelson's computer might try to send out this blob to Homer. It has a to, but it doesn't have a from field or a subject or a message. It's an invalid message. This message does not follow the email protocol, and therefore it's rejected by Homer's computer. In extreme circumstances, Homer's computer might even ban Nelson from the network and block his IP address altogether, just so he doesn't waste resources processing this kind of junk. Okay, so we've got this idea of protocol in place. So now we can start bringing this concept to Bitcoin. The goal of Bitcoin software, is to maintain for the user a database that matches everybody else's database. Homer, Bart, Lisa, and Nelson all have the exact same database on their computer. And somehow we want to create this situation just by sending messages back and forth and following a protocol. So let's start a bank. Everybody in this group has got some development experience and has written applications and is familiar with concepts like a database. So we're going to write a computer program that is a bank. And you can imagine the database looks like this. We really only need one table with 3 columns: usernames, passwords, and balances. So, you can see Bart has a username Bart, and his password is don't have a cowman, and he has 15 whatever units, rupees, dollars, and Lisa has a balance of 100. And this is all we really need to run a bank program. A transaction would look like this. We really only need 4 pieces of data to have a valid transaction. We need to know the sender, that sender's password, the recipient's name, and the amount that we want to send. And we only need to check 2 things about this transaction. Is the password correct? And does the sender have a sufficient balance? So we can run this program right here on the screen. Bart has 15 units, so that is enough of a balance to send 2 units to Lisa. And Bart's password is correct. So this is a valid transaction, and we can use that transaction to mutate our database from the state on the left to the state on the right. Password's correct, the balance is sufficient, so we can deduct 2 units from Bart's balance and add them to Lisa, and that's what I've demonstrated here. Bart goes from 15 to 13, Lisa goes from 100 to 102. Pretty simple. The problem with this model is that this column in the middle, password, is very, very sensitive. We have to keep it very secret. We have to keep it very safe. It definitely cannot be public. Nobody can access it. When transactions are transmitted, we need to be careful that the password isn't leaked. It has to be encrypted, or it has to be safe somehow. And the password can only be verified by one single central authority. And the motivation for this should be obvious. If Bart's password is public, then anybody can spend Bart's money, because that's how we've designed this program. So the problem is that you end up with an architecture like this. There's really only one database. It's only really mutated or controlled by one entity, the bank in this case. And clients can connect to it and send messages, but this isn't interesting. It's definitely not Bitcoin. So we're going to build on this concept. So to get to the next section, I'm going to define some terms from cryptography. Some of these are technical terms, but for the most part, I'm just trying to get these concepts across. And I'm going to explain some concepts that are not even used in Bitcoin. And the reason for that is because they're common cryptography concepts, and I want you to understand that they exist, but also that they don't exist in Bitcoin, because it can be a misnomer. For example, if somebody says that this transaction is encrypted in the Bitcoin blockchain, it's actually incorrect. And I'll explain why as we go forward. So symmetric encryption, symmetric as in two things that are the same on either side. In symmetric encryption, the sender and the recipient have the same key. So in the picture, I've got Bart and Lisa. They both got the same golden key. And Bart can take a message and encrypt it with that key. And what he gets from that encryption process is this unintelligible chunk of noise. And Nelson is looking at the noise, and it makes no sense to him. It's random gibberish. However, Lisa, who has the exact same key, can extract the message from that noise. So this is symmetric encryption. And, like I like to say about this, like, when we were kids, my sister used to pass messages to her friends in class, and they were encrypted with symmetrically. They each had a key, and like they had this set of symbols, and the symbols matched letters in the alphabet, and they would encrypt and decrypt with the same key. And if you have the key, you can encrypt messages and decrypt messages back and forth. I was trying to be Nelson. I was always trying to find the key so I can encrypt their messages to find out which boys they liked. Asymmetric encryption. So now we're going to have different keys on either side. That's why it's called asymmetric. So in this case, Bart has got the golden key. Lisa has got the black key with the yellow background. They're different keys. And each key has one function. One key is used for encryption, and one key is used for decryption. So this happens, in your web browser all the time. This is how Edward Snowden would send messages to Glenn Greenwald. Somehow Lisa's public key, the encryption key, is out there. It's in her Twitter profile, or my public key is on the first slide of this talk. So you could use that to encrypt messages to me that I can decrypt, but only me. And that's because I have the private key that goes along with that public key. So in this case, Bart can encrypt a message and it turns into random noise, and Nelson can't understand anything about it. And even Bart can't decrypt it. Once he's encrypted it, it's noise to him as well. He does not have the decryption key or the private key. Lisa does, and she can get the message out on the other side. So this is encryption, and it's really important, and we use it all the time in technology, but it is not used in Bitcoin, despite a common mistake that people will make about Bitcoin. And so the next concept is asymmetric authentication. And this is definitely a term that I have made up, but I think it makes sense, especially in this context. So it's asymmetric because there are two keys. Again, Lisa has the black key, Bart and Nelson have the gold key. And what we're doing is authenticating a message. So the message itself is not altered. It's not encrypted. Everybody can still read the message. But what Lisa does with her key is she adds a signature to it, the same way, if you just sign a signature with a pen. But it's a cryptographic signature, and she uses her private key to create that signature. And Bart and Nelson can use the public key to verify the signature. So I put my public key out there, and I can say, hey, this is a message written by Matt Zipkin, sign it with my private key, which only I have. And everybody else can verify it using my public key. Yes, Matthew Zipkin definitely signed this message. Or more appropriately, whoever owns the private key definitely signed this message. This is going to be very important in Bitcoin. And the last concept here is a hash function. So we are still taking data and turning it into unintelligible noise, but hashes are very different. So in a hash function, there are no keys. The input can be of any data, of any size. You can hash 1 byte. You can hash an entire encyclopedia. The output is always the same size. So hash is compressed data. The output is impossible to predict. It's always random looking, and it appears to be random. There's no way to know what the output of a hash function will be until you execute the hash function. There's no way to reverse it. There is no decryption at all. If you have a hash of something, there's no way to know what the original input was. The same input will always produce the same output. Now, this is especially key. So if I take the word Bitcoin and I hash it, and you take the word Bitcoin and you hash it with the same hash function, we will get the same output. And that's important, because if I tell you, like, here's the word Bitcoin and here's the hash, you can verify that that I did the operation myself, because there's no way to reverse a hash. There's no way to predict the outcome of a hash function. But if you have the same input and the same hash function, you will get the same output. So the emoji I like to use to describe this is kind of perfect, is this little chemistry set emoji. It takes a bunch of input, can be any amount of input, and it boils it and cooks it up and mixes it up, and out comes a little drop. And from that droplet, you can't know what the input was. So here, Bart and Lisa have the same input and the same hash function, and they both get the same output, this golden, noisy hash mess. So Lisa can verify that Bart did the same hash function with the same input data. However, Nelson, even though he has the same hash function, he has a slightly different input. It could even just be 1 bit different, and his output is completely different. So this is also going to be very important for Bitcoin as well. So just to kind of summarize, symmetric encryption, like my sister passing notes, we're not using that in Bitcoin. Asymmetric encryption, like Ed Snowden sending messages to Glenn Greenwald, we're not doing that in Bitcoin. But asymmetric authentication, where we sign messages, definitely important. And hash functions, where we compress data into an irreversible mess, also very important. So a user can prove that they know the private key connected with a public key. They can prove that by signing a message. And we have a way of irreversibly, unpredictably, and deterministically compressing data. So I'm about to move on. If people want to ask questions in the chat, I'm just going to keep my eye on it, but I'm going to take a sip here. Okay, great. So we've got some cryptographic primitives now, signatures and hash functions. So now we're going to make a bank. This time we're going to use cryptography, and we're going to try to improve on that model I showed you earlier where the password column is so sensitive. So here's a crypto bank database. Now, instead of having a username and a password and a balance, we're just going to have a public key and a balance. And what are we going to do with that? You can imagine a transaction looks like this. There are 4 fields: the sender's public key, the recipient's public key, the amount to transfer from the sender to the recipient, and a signature, cryptographic signature. And you can imagine that the signature signs a message made of the first 3 items. So it's authenticated in that way. We know that the sender definitely wants 2 units to go to this public key 1100 EAEA. So we do 2 tests. Is the signature valid? We do the cryptography. Yes, the signature is definitely created by the sender. Therefore, the recipient and the recipient and the amount, were definitely chosen by the sender. They were not malleated or altered in transit. And then we just check to make sure that the balance is sufficient. And here's an example of a database transition based on this transaction. The sender is 02BA, and they have a balance of 15, which is plenty, and they send 2 units to 1100, and that's what's happened here. The sender's balance goes from 15 to 13. The recipient's balance goes from 100 to 102. And so this is what we call an account-based model. And just for reference, this model is used in many cryptocurrencies, including Ethereum, but we're still not at Bitcoin yet, and we're getting there, because this is just sort of like the way to build up these concepts. We're not at Bitcoin yet. This is the account-based model. And it looks like this. So now our 4 characters, they each have their own private keys. Homer has got yellow, Bart has got green, Lisa blue, Nelson red. And they all have the same database because they all receive the transactions. Like I showed you here, they all receive the same transaction. They all mutate their database in the exact same way. They all verify the cryptography. And so we're getting close. Now we have this system where everybody has the same database. They create the same database by sending each other messages, and they can do it publicly by verifying these messages and cryptographic signatures so that nobody needs to keep a bunch of passwords safe. Okay, here's where we start talking about Bitcoin, and I love this transition. So the account model is what we're looking at on the left. Your bank, you sign into a bank, you have a username and a password. Even in the Ethereum account-based model, it's still kind of like this. You have a public key and use your signature to log in, and your account has a balance, which can be incremented or decremented. But actually, Bitcoin works a lot more like the picture on the right, where instead of tracking individual users and their balances, what we actually track are bits of money. And this is because Bitcoin was designed to be like cash. And that's what I have a picture of here. We have 3 units of money, 3 bills, you could call them coins, and each unit of money has a value and an identifier. So I've got 3 units here with values 10, 5, and 1. And this unit of $1 here on the top has an identifier B23825H63. So this is the model that Bitcoin is more like cash or coins. So this is what the Bitcoin database actually kind of looks like. We've got 3 columns, an identifier, a value, and something called a challenge, which is where things get really interesting. So keep in mind, these are not user accounts with balances. What we are tracking now in this database are units of units of value, coins. I'm going to start calling them coins now. Each coin has an identifier, a value, and a challenge. And if you're looking at these challenges on the screen, you can probably guess where we're going to go. Challenge for the top coin is sign this identifier with public key identified here, 2BA, like that. So the way that a Bitcoin transaction works is there are 2 arrays in a Bitcoin transaction. One array of coins that are going to be destroyed and another array of coins that are going to be created. So in this example transaction, I'm asking the database to destroy the coin with this identifier, and here's a response to the challenge. And then I'm going to create 2 new coins with a value and 2 new challenges. And to verify this, to make sure that our database is consistent with everybody else's database, we do these tests. First, we look at the list of coins to be destroyed, and we look at the identifier, 62A03142. That coin exists. That's good news. We passed the first test. And then the second test is, does the response satisfy the coin's challenge? The challenge for this particular coin is to sign a message with the public key 1100EAEA. And the response in our destroy coins array is 010386, blah, blah, blah. And so we use public key cryptography, asymmetric authentication, as I called it, to verify that this response satisfies a challenge. It results in true. That's good. And then finally, we just got to make sure that we're not creating any value, because this is a system of money after all, and Bitcoin is designed to not create money, at least in this way. So you can see the coin that we are destroying is worth 19, and the 2 coins we are creating on the left are worth 10 and 9 respectively. So we've satisfied all 3 of these tests. And so that transaction is valid and can cause the database transition that I've illustrated here. We are going to delete this coin 62A03142 worth 19, and we're going to create 2 new coins. One is called B2A0 and it is worth 10, and the second coin is called 13F11D40 and it is a value of 9. This is a valid transaction. This is the database transition that happens when this transaction is being processed. Okay, so that's the end of that concept. And again, feel free to ask questions. I'm just going to explain a couple things that I've left dangling here because I'm trying to be conceptual. And so if you're going to talk to people about Bitcoin, here's some stuff that I want you to keep in mind technically. We have this concept of change from a transaction. Let's say Bart wants to pay Lisa 10 Bitcoin, and Bart has control over a coin worth 19, like I showed in my example. For Bart to send Lisa exactly 10, what he does is destroys the 19 BTC coin and creates 2 new coins. One is worth 10, and the challenge there is to Lisa's public key. So she has control over the 10. And the remainder, the change, the 9 BTC, goes back to Bart's own public key. So he still keeps control over that. So you have your 19 BTC coin, you break it into a 10 and a 9 coin. Sorry, I'm not sure what happened there. You guys can still see my slides, right? I'm not sure why that.
Yeah, it still looks good.
Great, thank you.
There was a question and just a clarification. Shouldn't the value created equal the value destroyed?
Yeah, let me get there. Yeah. Shouldn't created value equal the value? Yeah, absolutely. The reason I said, oh, maybe you're calling me out because I wrote less than or equal to. And that's great that you noticed that. Really, really smart. And so in my example here, what I've shown is the values of the destroyed coins and the created coins are equal. 19 coins were destroyed, 19 coins were created. So why would you ever want to create less value? Wouldn't that be destroying value? First of all, that is allowed in Bitcoin. You are totally welcome to destroy value, just as long as you don't create any new value. There's an exception, and I'll explain where coins get created in the future in the next section. But there's a subtlety here too, which I didn't plan on talking about in this talk, but since you mentioned it. So in a transaction, if I was actually to send slightly, if I was going to create slightly less value than I destroyed, that remainder is what we call a fee, a transaction fee. And that fee is able to be collected and reallocated to a special type of user called a miner. And when we get to proof of work, this will make a little bit more sense. But so for now, the Bitcoin protocol rule is that you are welcome to create less value than you destroyed. You're always allowed to destroy value. We welcome it. It makes everyone else's Bitcoins worth more. And in some special cases, the value that's destroyed actually doesn't get destroyed. It gets reallocated to a special user called a miner. How do we decide the coins that we should destroy and doesn't have any impact on the fee? That's another great question. So what you're asking about is a concept called coin selection. And coin selection is a process executed by your wallet software. Bitcoin Core, for example, has a wallet with the coin selection algorithm. So does Bcoin. So does Bread Wallet, which is an app I have on my iPhone. And there are lots of strategies to it. And it gets a little bit more verbose because there is a bit of a marketplace in Bitcoin. There's limited blockchain space. And so users basically have to compete for that blockchain space by paying higher fees. So it's actually, that follows from the last question about what happens to the destroyed value. You're basically paying a fee for the transaction to the miner, and users are essentially bidding against each other by using higher fees to get their transaction to a miner. And we'll go into that a little bit later. So when you are choosing which coins to spend, it can actually affect the fee, because if your transaction gets too large, you may be required to pay a higher fee to get that transaction confirmed by a miner. So if you have 100 coins in your wallet and they're all worth 1 BTC, and you need to send 100 BTC, you're going to need to destroy all 100 of those coins, which means that this first array here is going to be quite large. It's going to include 100 coins. If you have 2 coins worth 50, you can still create a 100 BTC transaction, but you're only going to need to destroy 2 coins, which means that this array will be shorter. It will only have 2 items in it, and your entire transaction will be smaller. So coin selection is an advanced concept, and people are still coming up with new ways to do it optimally. And I'm pretty sure you guys are going to get into this as the course goes on. So is it like destroyed value equals created value plus fee? Exactly right. Exactly right. Yes. Yes. In the general sense. And when you guys get deeper into the woods on this, you'll find that there's other ways to destroy value that doesn't go to the fee, but that's the basic idea. Yeah. And I've just left fees out of this talk for now because it's just trying to get this concept, but I really appreciate that you guys are catching these details. So we talked about change. This is where we were. We talked about change. And then what else can you do with it with a challenge? So the challenges that I've shown you so far, basically a challenge is, what do you need to do to destroy this coin for everybody with a Bitcoin database to agree that this coin no longer exists? And the only example of a challenge I've given you so far is, sign this message with your private key. But as a matter of fact, Bitcoin has something called script, and scripts can be very exciting and very flexible. Not every coin and not every challenge is just signed with a public key. So you can actually create very complicated scripts. You can even create what you might call a smart contract. One example is multi-signature. So for example, maybe Jonas and I have a company together, and we create a wallet where the challenge for each coin is either Jonas or Matt can sign with their public keys, or we create a wallet where both Jonas and Matt need to sign. And so things like that can get much more interesting. And there's other things like time locks, where you can say this coin can be spent by Jonas tomorrow, but it can be spent by Matt only if 10 days have passed. Things like that. And then these primitives stack up to create things called the Lightning Network, which I look forward to you all learning a lot about. And I won't go into it now, but there's a lot of really exciting things you can do with these challenges. It's not just send this message with a public key. You can really do some interesting constructions with it. Okay, so these are the technical terms you guys are going to hear for the rest of your education in Bitcoin. When I say destroy coins and create coins, those are actually called transaction inputs and outputs. The word coin, you can use the word coin. It's also called the UTXO, or an unspent transaction output. The database that I've been describing thus far can also be referred to as the UTXO set, or the set of unspent transaction outputs. Basically, it's a list of coins that exist. What I've been calling a challenge can also be called an output script or a script pub key in the actual code. The response can be called an input script, or it can also be referred to as a script sig or witness. Those are the technical terms. You'll see those in the code. And what I've been calling a coin identifier is actually a combination of two values, a hash of the transaction and the transaction output index put together. So just this is the translation from the broad concepts I'm introducing to the actual technical terms other engineers are going to expect you to use. I see another question here. In a transaction in Bitcoin, public key of payee is known. So everyone knows to whom money is paid. That's correct. And people may not want others to know that. Okay, it's not entirely correct. So, and people may not want others to know that. Few other type of cryptocurrencies like Zcash and Monero offer privacy by using zero knowledge proofs, ZKP. Why doesn't Bitcoin do that? So it's true. The transactions that I've given you examples for, everybody on the network can see the public key. One thing you don't mention is that there's not really any way to know just by looking at the transaction who owns what public key. You could tell the world, this is my public key, and you could put it in your Twitter account, and people can look at the blockchain and see every Bitcoin transaction that's ever been sent to you. You can also not tell anybody your public key, and it'll be much, much harder for that type of analysis to be successful. The student is right. There are other types of cryptocurrencies that use more private technology to make the connections between public keys and real life individuals much harder. And actually, the ones that you've mentioned here, Zcash and Monero, do even more interesting constructions to blind the value of the transaction. So the other thing you didn't mention is that the transaction values are clear. They're not encrypted or blinded in any way. You can look at the Bitcoin blockchain and see, oh, here's a transaction worth $1 million, and it's going to this public key. And I don't know who that public key, I don't know who owns that public key, but whoever they are, they just received $1 million. Wow. There are other cryptocurrencies where even the values of the transactions are encrypted, and there's some really exciting cryptographic ways to maintain the validity of these transactions to ensure that no money is being excessively created. But to get your question, why doesn't Bitcoin do that? Because it's old, and because we haven't added that technology yet. And later on, I'm sure you will learn about governance and things like soft forks and hard forks. And there are ways to add new features to Bitcoin. They are hard though, because remember, the goal of Bitcoin is to ensure that everybody who is doing Bitcoin has the same database. So if we change a rule in the protocol, everybody has got to know about it. Otherwise, they're going to end up with a different database, and we'll have some problems. People will think money exists when it doesn't. I hope you guys learn more about this as you go forward in the course. But to answer your question as quickly as possible, zero knowledge proofs just weren't added in Bitcoin in 2009. I don't know if Satoshi even knew about it. I don't know if the cryptography was even ready yet. Some might argue the cryptography is still not ready yet, academically speaking. Is it possible to add these features in the future? Yes, but it'd be a remarkable challenge to do so.
Matthew, can I just jump in on that?
Please.
So I just want to add, I think the idea of creating a stable money is really important here. And Matthew pointed out some people might disagree that this technology is necessarily ready for prime time. Monero and Zcash are actually much smaller projects, and this entire ecosystem rests on a soundness principle that if Bitcoin were to break, this whole experiment may be over. Like this whole idea of actually running with the cryptocurrency sort of revolution or ecosystem, it sort of relies on the first. And so it's something to consider in terms of the trade-offs. These are all trade-offs. Zcash, for example, has some really interesting cryptography in it, but there's not 100% assurance that there's not money being created out of thin air because of the blinding that's done. Monero makes a different set of trade-offs. Zcash, these are different trade-offs to create a larger anonymity set and be able to create as much privacy as possible. They make different kinds of trade-offs. So, to ask a very complex question and want to receive a simple answer is a little bit naive. I think it's a good question. I think these are the types of questions that you should be asking, but these are all really complex trade-offs that are made. And maybe it's not like the Bitcoin core developers or Bitcoin developers don't want privacy. These are all sort of like bedrock principles that Bitcoin is built on. And yet, trade-offs have to be made.
Sure, thanks, Jonas. And it's also worth adding to that both Zcash and Monero have discovered inflation bugs, literally problems with their cryptographic systems where an attacker could have exploited the privacy functions to actually generate coins that should not exist. And in both cases, some analysis was done in Monero, they were able to prove that this had not occurred. In Zcash, they just think it hasn't not occurred because of the privacy. So thank you for that. Yeah, the soundness of the money is extremely important. Is there any way governments can collect taxes? You know what? I think this is sort of out of scope for this talk. Governments, at least in my country, my government expects me to tell them about my income and to report to them what I spend my money on and then tell them how much tax I owe them. And if they want to, they can investigate me. And if I've lied to them, then I can be in trouble. If you spend your entire life only using cash, there's no digital record of those transactions, you're expected to report, taxes to your government. So the next question, okay, this is pretty good. How does the UTXO database get communicated from one node to another, and what prevents a node to inject fake values in the UTXO database? Great question. So the database itself does not get communicated. The database is maintained by each user's own computer system, by their own full node running Bitcoin Core or similar software. The database is maintained by that software by sending transactions to each other. So just like, let's see if I can rewind here a little bit. So back to like this slide. Back to this slide. So if an invalid transaction is sent, if a rule is broken, if Nelson sends you a transaction that says, hey, I'm paying you 1 million Bitcoin and the inputs are worth 1 Bitcoin, your computer is going to be like, well, that's just invalid. It doesn't follow these rules. Where did I put the rules? Here, it would break this rule. So if you send an invalid transaction to a node, it simply gets ignored. And there are there's a concept when the nodes are connected to each other of nodes banning each other if there's too much misbehavior. And the Bitcoin developers are constantly trying to think of new attacks and ways to prevent them, adding features to the code that source exhaustion and denial of service and stuff like that. But the basic principle, and this is super duper important, is that the reason that I know that my Bitcoin database is the same as yours is because every time I get a transaction, I verify it. That transaction has to follow the rules. And if it doesn't follow every single rule exactly how it's supposed to, then I do not insert the transaction into my database. How much of the database does a casual user, a thin client maintain? Okay, this is a good question. So I have to check really quick, but the entire Bitcoin blockchain is something like, let's say it's 400 gigabytes. If you were to download the entire blockchain and store it on disk. The interesting thing about this, and I don't have this slide. I've given other talks where I'm talking to a general group, and I'll be like, okay, everybody knows what the data structure is, right? That's most important to Bitcoin, the thing that like verifies all the transactions, the most important thing you need to have on disk. And everyone's like, yeah, it's called the blockchain, but that's actually not true. It's called the UTXO set. This database, the list of valid coins, this is the consensus data. This is the most important thing. So let's say a block from 10 years ago has 100 transactions in it, and they create 100 coins. But then a couple years later, all 100 of those coins are destroyed. You do not need that old block anymore. And so you can run your Bitcoin software in a variety of modes. One mode is called an archival full node, and that means it downloads and keeps the entire blockchain and the UTXO set. Another thing you can do is called a pruned node, which means it only actually stores the last 2 or 3 days worth of blocks on disk, but it still maintains an entire UTXO set, and therefore it can still verify every coin in the database and send and receive transactions just as accurately as the archival full node. And a prune node only needs 10 gigabytes or less. It's actually probably more like 2. And then finally, there's a such thing called a light client, which does not maintain a UTXO set. And it uses other tricks to sort of guess that things are valid with a high probability. So there is some trade-offs. If you're using a light client, like I have an app on my phone called Red Wallet, and it does not store the entire blockchain, and it does not store the entire UTXO set. And if somebody really, really, really wanted to steal from me, they could trick this wallet, but it's a very expensive attack. They could send me invalid data that that the light client wouldn't have the resources to actually verify. And so for that reason, I don't use this wallet for, a huge amount of money. It's like $100 maybe, the kind of cash you would maybe keep in your pocket. If you lose your wallet, that's a bad day, but it's not the end of the world. So there are some trade-offs with how much data you store. And the trade-off is the privacy and security of your software. Is there a certain amount of UTXO transactions just waiting for a long amount of time, like those transactions which don't have any rewards? Okay, that's a good question. I'm going to skip ahead real quick on this, but there can exist a rogue node which might be skipping verification and just Okay, so I'm going to answer the rogue node question first. Go ahead and set up a rogue node and send out as many invalid transactions as you want. They will not be accepted by my computer. You can send them to Coinbase or an exchange or anybody. You can go to a website that sells t-shirts for Bitcoin and try to send them an invalid transaction. You just won't get your t-shirt. What's probably likely to happen is that your computer will just get kicked off the network. You won't be able to connect to anybody. You connect to my node and you're like, here's an invalid transaction. And my node's like, well, that's invalid, so I'm not going to talk to you anymore. Your IP address is banned. Can we compare UTXO with IPFS? That's a little abstract. Okay, here's what I'll say about this. IPFS, interplanetary file system, I think, is a type of cloud storage that is theoretically decentralized. You can upload your files to basically somebody else's computer, to a bunch of other people's computers with a certain amount of reliability that you'll be able to get that data back. And once it's on the system, other people can access it as well. So can we compare UTXO with IPFS? I'm not really sure because they're two different things. UTXO set is a database that I keep on my computer, and IPFS is a public data storage system. What I will say about this, though, is the UTXO set is incredibly sensitive because it is how you know that money that somebody is paying you is real and not counterfeit. And so you don't really want to share your database with somebody. You don't want someone to have access to it. Even if I put my entire UTXO set on IPFS, I wouldn't want you to trust it because I could add extra UTXOs into it. I could be like, oh, by the way, this public key has a Bitcoin worth 1,000 Bitcoins. And it happens to be my public key. And then I'll send you a transaction and you'll look at the database on IPFS and you'll be like, well, the coin exists in the database, everything's valid. So I guess this is a valid transaction, but it's not, it's a lie. So you wouldn't want to share your UTXO set with somebody that's sensitive. Okay, and then back to the question about UTXO transactions waiting for a long period of time. This is actually going to end up being a little out of scope for the talk, but since I did mention that there is a marketplace for inclusion in blocks, which we haven't got to yet, yes, it's possible. If you do not pay a big enough fee, it may take a long time or possibly forever for your transaction to be confirmed. You guys will learn about this later. Can privacy be compromised to an extent if some nodes start linking addresses with IP addresses? This is a great question as well. So you, if you set up a Bitcoin node and you connected to 1,000 other peers, so you got a big computer, let's say you connect to 2,000 other peers, you're connected to every node on the Bitcoin network, and you know where transactions, you might be able to guess, I should say, where transactions originate from. Like, oh, the first time I saw a transaction came from this node over here in New Delhi or something, at this address, this IP address sent this transaction. There's possible chain analysis there. You could possibly link that transaction with the node who sent it. And Jonas actually might need to jump in here and update me on this, but there are a lot of proposals for ways to abstract this. There's something called, I think it's called Dandelion, and other cryptocurrencies have attempted to implement this. But there are ways to like secretly pass around a transaction, and then it gets broadcast from a remote node. The other thing you could do is just run your Bitcoin node behind Tor, or create a transaction on your computer and then do whatever you want, put it on a postcard, mail it to your friend in a different country and have them broadcast it, you know? So yes, with enough power, an attacker could detect the source of transactions being broadcast on the network, but that kind of attack can be mitigated. And, yeah, that's all I'll say about that. Is it possible to derive UTXO set by processing the block database? Exactly. And in fact, I would go so far as to say the only way to derive the UTXO set is by processing the block database. And maybe I should make this explicitly clear in the slide. If you want a complete UTXO set, you must verify every block in the blockchain. So even if you don't store all 600 gigabytes on disk, you do need to download them all and verify them all to make sure everything follows the rules. And that's how you end up with the same UTXO set, the same database as everybody else on the network. Isn't there some kind of transaction timeout which will remove transactions from the mempool? Yes, so this is what's called policy, and everybody who runs a Bitcoin full node can configure their own node sort of flexibly like this. So you might decide that you never ever drop any transaction from your node, that you keep them all forever. Other nodes may be configured that like, okay, you send me a transaction, I'm gonna hang on to it. And if it doesn't get confirmed in 2 weeks, I think is actually the value in Bitcoin Core, it might be 3 weeks. If it doesn't get confirmed in that amount of time, I'm just gonna forget about it. I'm gonna delete it. And you can send it back if you want, but there is this concept of dropping transactions that do not get confirmed within a minimum amount of time. Coco here has asked lock time. That is, we haven't quite got to lock time, but or I did sort of mention it. What else can you do with the challenge at time lock? Okay, so what I'll say about lock time is that when I say this thing about how coins have challenges, this coin can be spent by whoever owns this public key. You can add other characteristics like this. Like this coin can be spent by anybody, by whoever has this public key only after this amount of time. And some really interesting constructions can be made this way, where like I can create a payment where Coco can spend that coin immediately, and Jonas can also spend it, but Jonas has to wait 10 days. And then Jonas's spend will be valid, that you can add that kind of protocol rule. And there's lots of other interesting constructions you can do as well, like hash locks, where you need to provide a valid signature, but you also need to provide the input that produces the same hash output, and all kinds of crazy stuff. It's very exciting. Okay, I'm going to push forward, but all these questions are great. It really shows you guys are paying attention and asking really interesting stuff, and I can tell you're all really ready to get into the details. Okay, so here's an example of an actual Bitcoin transaction in JSON format. There's a lot of data here that is being translated for me, the user, in the user interface. Not every byte you see on the screen is actually in the transaction, but this is like the program has generated some details for me as well. Up at the top is the TXID, that is the hash of the transaction. Version and lock time are sort of metadata. I'm gonna skip to the bottom real quick, and you see size, weight, fee, status. These are data that are evaluated, computed by Bitcoin Core in this example, and just showing you different statistics about it. The fee is calculated, but actually the fee itself does not appear in the transaction itself. As we've discussed, the fee is a difference, is coins that are destroyed but not recreated. So this program has calculated the fee for me and displays it for me. The interesting thing here to see is V in and V out, which are the inputs and the outputs to the transaction, or the coins being destroyed and the coins being created. So in this example, we are destroying one coin. The identifier is there, the TXID and the V out at the top there identify the coin. The script pub key is there. That's what you could call the challenge. And the challenge has been translated for us into a series of opcodes, duplicate a piece of data, hash the data, and that has a certain meaning. The script sig is the response that is used to verify that this owner has, that this coin owner, that this user owns the coin and has signed with their public key. That's a valid spend. And then at the bottom, it's a lot simpler, the outputs. These are the coins that are being created. There are 2 here. And the script pub key is the challenge. This is saying, you know, this is the person who needs to sign for this coin if they want to spend it, and likewise on the second one. And what's interesting about this transaction is the 2 coins we are creating, the 2 outputs, actually have different challenges. One is a script hash output, and the other is a public key hash output. And I'm very excited for you all to learn about that, because it kind of goes back to what I was just saying. There are different types of challenges. A public key hash is very simple, sign this message with your public key. And the script hash, things can get much more interesting. That's where you can get stuff like time locks and Lightning Network. Is there a possibility of collision in transaction hashes? That's a great question. And I'm going to put a pin in that for now. I'll just refer you back to the beginning when I was defining hash functions. Remember, we have 32-byte output. That's 256 bits. That is a really big number. 2 to the 256 power is an astronomically large number. So the likelihood of finding 2 inputs, we're talking about hash function now, not a Bitcoin transaction. I got a hash function, and I've got an output, and I need you to find 2 inputs that produce the same output. And you can think about it, but as I said, hash functions, good hash functions, the hash functions that we use in modern era cryptography, produce unpredictable random output. And so we'll get to this a little bit later. But to answer your question, is a possibility of creating a collision in transaction hashes? For all intents and purposes, no. And on an emotional level, I sure hope not, because we're in big trouble if that happens. And then on a more subtle note, there have been colliding transaction hashes, but it's an interesting subtlety, and it won't happen again because a rule was added to the protocol a long time ago. Yeah, okay, I'm sure Jonas has got the link there. So I'm going to move on. Okay, so are we done? We can use asymmetric authentication cryptography to maintain a database of spendable coins that anyone can access. If a transaction signature is valid, we update our database. Transactions go to all the Bitcoin nodes on the network. So we should be done, right? You know, we all have databases. We send transactions to each other. If a transaction is valid, I update my database. You update your database. We all have the same database. That's it. We're done. Or are we? Or are we done? Maybe you're thinking, yeah, sure, we're done. That's it. We've created a crypto bank that uses units of money instead of accounts. But we are missing something important. And this is where things are starting to get really interesting. What is the truth? What if Nelson broadcasts 2 transactions that destroy the same coin, but create 2 different sets of coins? Which one is real? Who did Nelson pay? So in this example, Nelson's got his private key here in red, and he owns a coin called coin A that he can sign for with his private key. And he creates 2 transactions at the same moment. On the left case, he creates a transaction that creates coin B and pays Bart for a cup of coffee. And on the right side, he creates a transaction that creates coin C, and that pays Lisa for a book. So Nelson only has, let's say, 1 Bitcoin, and he's able to send 1 Bitcoin to Bart and to Lisa. He's able to create 2 transactions that are both valid. We're trying to create a system of money here, and Jonas emphasized that soundness principle. So right off the bat, like, there's obviously something wrong here. Who did he pay, Bart or Lisa? Should they both ship their products to him, or how do we know which one is the lie? And to answer this, we're going to talk about proof of work. This is where proof of work comes into the conversation. And I see you asking questions. I'm going to get through this section, and then I'll come back and we'll address these questions. Okay. Let's talk about hash functions. An example hash function is SHA-256. SHA stands for Secure Hash Algorithm. It's old technology, and 256 means that the output of this hash function is always 256 bits. Not every hash function outputs this exact size. There are lots of other hash functions out there, Blake2B, for an example. Okay, so let's review hash functions, and specifically SHA-256. No matter what the input data, whether it's 1 byte or an entire encyclopedia, the output will always be 32 bytes or 256 bits. The output is indistinguishable from random noise. There's no pattern to it ever. The same input always produces the same output. The function cannot be reversed. If I give you a hash, there's no way to know what the input to the hash function was. But an input-output pair can be verified by anyone very quickly. If I give you a hash, and then later I give you the input, then you can just do the hash function one time, verify the output is the same, and you know that that input hashed to that output. So here's some examples of the output of SHA-256 as I type the word Bitcoin in. So the hash, the SHA-256 of the letter B is this first row, BI, second row, and so forth. So the important takeaway from this slide is as I add bytes, characters, to the input string, the output string, the 32-byte SHA-256 output, is vastly different. Look at how different these are. Even though the inputs are very similar, the outputs are remarkably not similar. However, there is one thing I want you to notice, which is the hash of BI, here the second row, and the hash of BITCOI, the second to last. They both start with 6B. Okay, so everything is basically random, but there is a 1-byte collision here. We could say there's a 1-byte collision between these two inputs. Out of 32 bytes, these two inputs have the same first byte. Okay, that's interesting. So what is the input for this hash? I put a SHA-256 output here on the screen, and I want you guys to all tell me what data I hashed to find that input. And this kind of goes back to the question of can two transaction IDs have a colliding hash? Like, good luck, right? You might need to process 2 to the 256 input attempts to figure out exactly what I hashed, or to at least find another piece of data that produces the same hash on the output. Okay, 200 to the 2 to the 256 is such an astronomically large number. There's not enough time or energy in the universe for you to accomplish this feat. It's for all practical purposes, it's going to be impossible. This hash, the only way for you to know what the input for this hash is if I tell you what the input was. Then you can verify it. Okay, well, what if I said, what is the input for, what if we only care about the first byte? So you can provide for me any input that when I put it into the SHA-256 function, the first byte will be DA in hexadecimal. That's only 8 bits, right? So you can probably find a solution with only 256 attempts, because remember the hash function is always random, so it's like flipping a coin. So it's similar to flipping a coin 8 times and getting tails 8 times in a row. That doesn't sound impossible. In fact, if you wanted to do this, you could probably accomplish this feat in, I don't know, an hour. Maybe it takes you a day to flip a coin 8 times and get tails each time. So if you want to find the input for SHA-256 hash that starts with this 1 byte, that's easy. Okay, what if I wanted you to find the input for a hash that started with all these zeros, 76 bits worth of zeros? Now that's starting to get a lot harder, right? This is an actual hash for a Bitcoin block at height 666,208. Back when I was making the slide, that's the actual hash. And what we see here is a partial collision of 76 bits. Somebody found a piece of data that when hashed with SHA-256 produces this hash, this output, and it starts with 76 0 bits. So if I told you to find input to a hash function where the output hash started with 76 bits of zeros, how many attempts would that take? Well, at the time I made this slide, the Bitcoin network hash rate was this ridiculous number, 147 exahash, or maybe it's petahash, I'm not sure. It's dropped a little bit over the past couple of weeks, but it's still an incredibly large number. This is the amount of coins, the entire global Bitcoin mining system. This is the amount of times that we are flipping coins. And we're ending up with getting 76 coin flips of tails in a row. And so this is so hard to do, even with the entire planet of Bitcoin miners hashing away at this crazy number of hashes per second. It still takes the Bitcoin network 10 minutes to find input to the hash function that produces this output with that many zeros. I hope that's clear. It's kind of crazy to think about, but you know, if you flip a coin 8 times, you get tails 8 times, that's easy. You've now collided 8 bits. But now if I ask you to collide 76 bits, it's going to take you the entire planet worth of computing power, 10 minutes, to find a hash that starts with 76 bits of zeros. Okay, So that's proof of work. Before I go into bringing this back to Bitcoin, I'm going to check the questions. I heard that quantum computing could break SHA-256. That's actually not my understanding. And I could be wrong. This is outside my area of expertise. But my understanding is that quantum computers are good at breaking things like asymmetric cryptography, which are math-based. A quantum computer, as far as I know, cannot break SHA-256 in the way that it applies to Bitcoin, and that it would make enable miners to cheat or to find an input faster. I don't think that applies. If quantum computing gets to the point where it can process large amounts of data, cryptography is at risk. Every encrypted messages on the internet is at risk, and we're in big trouble. But not mining, not the hash function itself, as I understand. In Coinbase transaction, the block reward is the same. If some miners get selected, won't the same transaction be created? In that case, one hash be the same. Okay, that's a good question, and these are the details I didn't want to avoid. This is another question about creating a transaction, two transactions with the same ID, and you got it. Yeah, very clever. You figured out a way for two transactions to exist with the same hash, and this has happened on the Bitcoin network. There are two pairs of transactions with the same TX ID. And first, I'll explain how we stop this from happening. Basically, what we do is we require every Coinbase transaction to also include the height of the block in the Coinbase transaction, in a part of the Coinbase transaction that is otherwise ignored by the protocol. So that forces every Coinbase transaction to be unique, and we'll never have this problem again. But what's interesting about it is, before this was enacted, this is a rule called BIP 30. You can look it up. I think Jonas might have added a link to it here in the chat. But this has happened before. And because if you think about the way the database works, how we insert coins into the database by their identifier, what happens when you produce a transaction with an identical identifier to a transaction that already exists is you replace it. You replace it. So in the two cases in Bitcoin's history where a duplicate transaction ID happened, the original transaction with that ID no longer exists. The duplicate has replaced it in the database, and so the original transaction doesn't exist. It can't be spent. It doesn't exist. It's been wiped out by its replacement that has the same transaction ID. Isn't that interesting? I think the probability of collision is around 50% when we compute. Okay. Yes. Okay, I think you're right. You're very, very clever here with the square root of 2 to the 256. What we're talking about here is the birthday problem. And you're right. I should update my slide. I was exaggerating by saying it might take you 2 to the 256 attempts to collide the hash. Actually, I think it still might. You're bringing up the birthday problem, which would be stated more like this: find me two inputs that produce the same hash output. That's the birthday problem, and you're right, it's root n. But what I'm talking about is I'm giving you an output, and you have to find an input that matches that specific output. So it's not quite the birthday problem, and I think it's more like how I estimated it. It would take you 2 to the 256 attempts. With very fast GPUs coming every day in the world, we've seen big tech. How does Bitcoin ensure that there won't be such a case here? I'm not exactly sure what you're asking.
I think maybe this is a difficulty adjustment answer.
Okay, sure. Okay. And how is the 10 minutes to find the hash fix? If more judges, okay, and another, how do we know the collision of the TXID happened? I'll just answer the TXID collision. It was just visible on the network. All the transactions are visible. I don't have a great answer for that. I don't know exactly the story, but if you look up BIP 30, Bitcoin Improvement Proposal, I'm pretty sure it's BIP 30. I think it was written by Gavin Andreessen. I could be wrong about that. They just simply observed this happening. They're obsessed with Bitcoin. They were watching things happen. They noticed this collision and they decided they needed to prevent it. Okay, so the 10 minutes thing, and also the adding hash rate to the world and making this hash rate go up. So this is something that I've left out of this slide because I intended it to be more of an entry-level talk, but I'm very glad you asked that question, and I'll explain difficulty adjustments, as Jonas called it. So the slide that I have up here has one hash, and I'm telling you that to find this hash, you need to collide with 76 bits. How did I get the number 76? Why did I tell you 76 bits? Will it always be 76 bits? With this hash rate, will it always take 10 minutes to find this collision? Well, first of all, if this hash rate that I have on the screen, 147 exa or petahash, if it takes that hash rate 10 minutes to find a 76-bit collision, it will probably always take 10 minutes for that hash rate to find a 76-bit hash collision. However, what if this hash rate goes up? The Bitcoin network needs a way to simply require more bits. If the hash rate goes up, then we need a way to say, okay, it's not 76 bits now, it's 78, it's 80, it's 82, it's 105 bits. And actually, yeah, I'll add this slide in the future next time I give this talk, because it's a good question. So the hash I have here is 76 bits. If you were to look at Bitcoin Block Explorer and look for the hash at block number 100, okay, a hash of a block from 10 years ago, probably mined by Satoshi Nakamoto, something really low, you will not see 76 bits of 0 in the front. You'll see probably more like 30. And that's because in Bitcoin, we have a concept called a target difficulty. And that target difficulty changes over time based on the hash rate. One of the protocol rules in Bitcoin, and by which I mean a strict protocol rule, something that has to be satisfied for data to be valid for us to update our database. One of the rules is that the block target time should be on average 10 minutes. So here's what we do. Every once in a while, okay, it's every 2016 blocks. It takes about 2 weeks. The Bitcoin software will look at how long it has taken the network to produce the last 2016 blocks. And if the amount of time has not, and each block has a timestamp, a Unix timestamp. So we know when each block was created. And there's rules about how flexible the timestamp can be too. So don't worry, we've got that covered. But basically what we do is we look at the timestamp of the block 2016 blocks ago. We figure out how long it took the network to generate 2000 blocks. That way we can estimate the hash per second of the network, and then we use the hash per second estimate of the network to decide what the target difficulty should be for the next 2 weeks. And in that way, the target difficulty of Bitcoin adjusts up and down in an attempt to maintain an average 10-minute block time. And if you Google, if you search on the internet for Bitcoin difficulty chart, you can see it go up and down over the last 10 years. For the most part, it's always gone up. There's been a couple dips. Difficulty is always getting harder because people are deploying better hardware, more hardware that is boosting the hash rate. Although what's interesting, if you guys are aware of the news lately, there's been some new rules in China where a lot of Bitcoin mining happens. And a lot of those machines have shut off. And so the Bitcoin hash rate has dropped this month, and the difficulty has gotten easier. The difficulty target has gone up. The difficulty level has gone down. And when people shut these machines off, it takes longer for 2000 blocks to be generated because there's just not that many hashes per second. So it might take 15 days or 16 days for 2000 blocks to be generated. At the end of that period, the software makes a calculation and says, oh, okay, blocks are coming out pretty slow. Let's change the difficulty target now that we know the new network hash rate, and we'll get back on the 10-minute thing. So as these difficulty adjustments are being made, you can actually see block production speed up or slow down. The 10-minute interval will get faster or slower, and then this adjustment is made every 2 weeks, and then bam, we're back to basically about 10 minutes. Okay, how do we know the collision of the TXID happened? Again, it's there's probably a Bitcoin talk thread. I think Jonas posted the link to it. People who are obsessed with Bitcoin just observed it happening on the blockchain. I'm not sure the actual story. How is the replacement of transaction ID possible if same transaction is generated again? Isn't the blockchain immutable? Okay, I'm going to answer the 10 minutes thing. This is something that Satoshi just decided. I'm not sure if there was any, I don't know if he discussed with anybody what it should be. I've heard one explanation for this, which was relayed to me by a former contributor named Mike Hearn, who apparently got an email from Satoshi himself asking this question. And I learned this from Mike Hearn on Reddit. And the answer, as it was explained to me, is simply this, that let me see if I can remember. It was basically, the idea was like, it takes 1 minute for a block to propagate around the world, to propagate around the network. And so Satoshi decided that that 10% of that wasting 10% of hash energy was acceptable to him. So I don't know. I mean, I don't know. There are other cryptocurrencies where it's not 10 minutes, it's 1 minute, and there's more fork chains, and you can pick your own constant. 10 minutes has proved to be a pretty good value. And like I said, the explanation that I got, whether you believe it or not, was that because blocks take a while to propagate around the network, some miners in different parts of the world will be wasting energy because the block has already been discovered. They're still working on the same block. And then, it took a minute for that to get to me. I just wasted the last minute looking for the right hash. And okay, so supposedly Satoshi told Mike Hearn, who told me on Reddit, that 1 minute of wasted hash is an acceptable value. How is the replacement transaction ID possible? So the blockchain, okay, so this is a good question. And just to be clear again, the blockchain and the UTXO set are different data structures. The blockchain is a set of data, and the UTXO set is the data structure that really matters. You use the blockchain data to create the UTXO set. So the blockchain might have 2 transactions with the same ID. The UTXO set will not. It will only have 1. So when the duplicate transaction came in on the blockchain, it replaced the one that already existed in the UTXO set. I heard there's about 100 years until the last block will be mined. Unix epoch time. Okay, these are 2 different things that we could talk about. The Unix epoch time. I believe that so this question is about the timestamps in the Bitcoin blocks, which are, I don't want to embarrass myself here, but I want to say it's a U32, which is 4 bytes, right? I hope I'm not embarrassing myself, but some systems, so that means that there's a point where timestamp is going to roll over, right? And it would be the year 2038 if those 4 bytes were a signed integer. Of course, you can't have a negative timestamp. So if you interpret those 4 bytes as an unsigned integer, the rollover is actually pushed back to something like, I want to say 2140 AD. I was actually just looking at this issue on the Bitcoin Core GitHub this week because I had a question about this, and people are discussing it already, what we're going to do. We have plenty of time to fix it, and it might not even be a problem depending on your operating system. I'm not sure. In 100 years, the last block will be mined. This is not true. There's nothing stopping blocks from being mined ever. The thing that will sort of stop in 100 years, let's say, is new coins being generated. And I'm going to get to that in a couple of slides. Remember, in the beginning, I said one of the protocol rules for Bitcoin is that there will never be more than 21 million Bitcoin in existence. And we're not there yet. In 100 years, we will be. And then what's going to happen after all the coins are generated? We can still mine blocks, don't worry. Is 2 weeks a good duration for changing the difficulty? Jonas has got a great answer. It's worked so far. It's true. Other blockchains have messed with this. Some blockchains retarget the difficulty every block. Something very interesting about the 2-week value, however, is this. If there is a fork in the blockchain, let's say somebody, let's say half the community, let's say, for example, hypothetically, in our imagination, that half the community decides to break a rule, like what the maximum block size is. And people start mining different sets of rules, incompatible chains. Okay, let's see if I can explain this. I haven't tried really explaining this super well. The fact that it takes 2 weeks to adjust the difficulty means that if 10% of the miners decide to create their own fork, an incompatible protocol rule breaking fork, they're the minority hash rate, they split off the blockchain. They will be stuck with Bitcoin's difficulty adjustment rules, which means if they only have 10% of the hash rate, it's going to take them 100 minutes. I hope I'm right about this. I might be getting the math wrong. If they have 10% of the hash rate, it's going to take them 100 minutes to find the next block. And then 100 minutes after that, the next block. And it's going to take them, they still have to go through 2,000 blocks before the difficulty adjusts back to a point where they can mine every 10 minutes. So the 2-week difficulty adjustment interval, whether or not it was intended to do this by Satoshi, actually prevents minority hash power from having successful blockchains. And I hope that makes sense. I should maybe add a slide about that too. But that's the idea, is that it takes so long to adjust the difficulty that if you don't have enough hash rate, it'll take even longer. Like it'll take months to get the next block. And so those, the minority blockchains just die, ideally. Why is there an upper limit on mining Bitcoins, and why 21 million? Why is there an upper limit? This is something that goes back to the soundness principle that Jonas mentioned. It's a cultural property. It's a social property. People want, they want a monetary system that is, some people, I'll say, Bitcoiners for the most part, want a monetary system that is not inflationary. And there's economic reasons behind this, not technical reasons, but economic reasons that Satoshi mentions. I don't know if he mentions in the white paper, but definitely talks a lot about it in the early days on Bitcoin Talk. And a lot of Bitcoiners will tell you that one of the most interesting properties about Bitcoin is that it has a hard upper limit on the amount of money that can be generated, and it is not inflationary, and it has a lot of really interesting social and economic properties. Why 21 million? This is another great question. I'm not going to answer, but you can look it up and people have discussed it. There might be some properties about like the 21 million Bitcoins plus the 8 decimal places fits perfectly into like a U64 or something like that. Out of scope. I hope you find the answer to that though.
Hey Matthew, I know these questions are great, but I also want to make sure that we're respecting everyone's time, including your own. And
great.
So maybe
okay.
half past, we can wrap that.
Okay, sure, no problem. I just got one last section. These questions are so good though. I'm really enjoying them. All right, so we got proof of work. You guys know how proof of work works now. Now we're going to bring it back to the beginning of this section. Remember, was this, okay? Nelson has created 2 valid transactions, but from a monetary perspective, only one can be valid. Either Bart got paid or Lisa got paid. And then I explained what proof of work is, and now it's time to use proof of work to protect Bart and Lisa from Nelson. So here's how we use proof of work in Bitcoin. We have this thing called a block. This is the first time I mentioned what a block is in this talk, really officially. A block is composed of 3 things, basically. It's a list of transactions. It includes the hash of the previous block, and it includes a nonce. A nonce means number used once. It's a number that is chosen by whoever is making the block, by the miner. And the nonce is what we're going to use to go through all these hashes per second to try to find a valid block. So a block is a list of transactions combined with the hash of the previous block and a nonce. Every nonce results in a completely different hash without changing anything else. So when you are mining a block, you start with your transactions and the hash of the previous block, and then you hash it and you look at the outcome. And does it have those 76 bits? Does it meet the target difficulty? No. So we increase the nonce. We start with 0, then 1, then 2, then 3, and we go and go through 174 peta nonces per second, trying to find nonce that makes the hash of this block satisfy the target. And that's when the block is valid, and you can send it to your peers and they will evaluate it and do the hash one time and verify that it's correct. So the other interesting thing about valid blocks is they are allowed to contain a special transaction that we've already sort of chatted about here. The transaction creates coins, but it does not destroy any coins, meaning that the money supply is incremented and rewards the miner. So there is a reward for finding the correct hash. And that's it. That's the game. So go do it. One interesting thing to note is that in my diagram here, I've shown these 3 blocks with arrows pointing to the previous block, and Satoshi's white paper, they're pointing the wrong way. What a dummy. Just kidding. Okay, so chain work is the next concept for this. And what chain work is, that we'll call it, this is abstract, but we're going to call it the total number of 0 bits in the hash of every block in the blockchain. So the important concept here is that as we add blocks to the chain work is accumulative. So that the chain work we have in today's blockchain is way higher than it was 5 years ago, 1 year ago. Chain work always goes up, not just as the chain gets longer, but because the difficulty will adjust, and I'm glad we talked about it. The target will change, the number of 0 bits you need to get to have a valid block will change, and therefore the total number of 0 bits in the entire blockchain goes up. So here I have 3 blocks. The first block has a hash of 0f that starts with 4 bits. The second block has a hash of 00f, that's 8 bits, added to the 4 from the last block. Now we have a total chain work of 12. And then on the last block, we've got 0000, that's 16 bits, plus the 12 we already got from the last block. Now we're up to 28. So every time you add a block to the chain work goes up, and it goes up by basically how hard it was to find that block. Okay, so let's go back to this now. We're going to tie this together. Nelson has 2 transactions. We want one to be valid. We want one to be invalid. Which one of these transactions is true and which one is the lie? So here we have two blockchains, let's say, that both started from the block on the left, and then miners have created two histories. And the blockchain on top contains transaction I, which is going to Bart, and the blockchain on bottom contains transaction N, which was going to Lisa. Both of these are valid in and of themselves because they are different histories. So if you are only aware of the top blockchain, your UTXO set will be consistent. Transaction I is the truth. And if you only have the bottom blockchain, transaction N exists and is valid. And they both, pass all the validity checks that we talked about earlier. So how do we know which one of these blockchains is the truth? Which transaction is correct, I or N? And the answer is simply whichever one has the most accumulated proof of work. So the top blockchain, if you add up all the zeros, has a chain work of 28, and the bottom blockchain only has 16. Therefore, the blockchain on the top, ending in block 000 FBF and containing transaction I to Bart, is true. And if everybody on the Bitcoin network follows this rule, we will all have the same database. And so in that case, here's what it looks like. Everybody has the same database. It's green. It matches the blockchain I have on the top here. Bart has been paid. Lisa has not been. When Lisa receives transaction N from Nelson, she knows that it's fake. It's counterfeit. It's invalid because the coins he used to create that transaction have already been spent. They've already been destroyed to create the transaction to Bart. And that's it. That's how we do it. So, obviously this requires everybody on the network to be aware of both blockchains, or more importantly, to be aware of the blockchain with the most accumulated proof of work. And this is what engineers are working on every day in Bitcoin Core to ensure that if you are running a Bitcoin full node, you are finding the chain with the most proof of work. And that if somebody is trying to hide that chain from you or feed you a chain with less work, we need to mitigate that in the software at the networking level. So this is it. The point of the entire talk comes down to this slide, the Bitcoin full node. The purpose of the Bitcoin full node is to connect to other Bitcoin full nodes on the internet and exchange transaction messages and blocks in order to maintain for the user a database that matches the database of every other full node. And you can say that your node is in sync when it has satisfied this, like provide for the user some confidence that I know the blockchain with the most accumulated proof of work. And so I know the state of the system. And when you're in sync, then you know with confidence, high confidence, that your UTXO set is correct. It matches everyone else's UTXO set. And that's how you know that when Nelson sends you money, that it's valid. And that the money that he sends you, you will be able to send to the next person. And that's it. That's the end of the talk. So bitcoin.stackexchange.com, that's where to go for your questions. I'd say I just want you guys to know about this link. It's been around for years, and there's tons of great questions there that you probably have that have already been answered by really smart people. And if you think of some new questions, I really encourage you to create an account on Stack Exchange and ask them there. Of course, you guys are also going to be mentored for the remainder of this program. So that's good too. So that's it. Does anybody have any more questions? What happens if someone generated an input which has more zeros when hashed than the difficulty? Nothing special. Nothing special. All you need to do is satisfy the target. It's literally in the code. It's a less than or equals. And if that returns true, your block is valid. There's no special reward for block hashes that exceed the difficulty by any amount. Other blockchains have explored concepts with that. And actually there's interesting fast sync methods where what you're describing will happen a certain amount of time. And because of that, you can sort of skip validating some data. It's deep. That's a good question, but the answer is it doesn't really matter. Great. How's everybody feel? What are we thinking? I got 5 more minutes left. If anybody has any more questions, or Jonas, if you want to add anything.
I think this was great and exactly what we needed. So thank you so much. I do want to cut it at 1/2 past. There's one question about what if a node goes offline for some time? Like how does it resync?
Sure, good question. Remember, the goal of the full node is to find the chain with the most proof of work. And not only will your node do this after you get back online, but you can also imagine, let's say that China decides to cut off its internet from the entire rest of the world. And then we have two Bitcoin systems running in parallel, both mining. You know, we don't know which, there's two basically competing. Basically, China, we could say, has shut down. And then one day they connect again. They will heal. They will heal. One chain has more accumulated proof of work than the other, and that chain becomes the truth. If the two chain splits get too long, it'll be really interesting socially to see what happens. But as far as the software goes, we just find the chain with the most accumulated proof of work, and we get there and we make sure our database is consistent with it. So that's a great thing about a Bitcoin full node. And actually this works way better with proof of work than proof of stake, which we did not talk about. But eventually, if you get into arguments with somebody about proof of stake, this is something that proof of work does really well. You turn off your computer for whatever, a year. I mean, I've done this. I've got full nodes I haven't run in a while. When you turn it back on, your node will go back on the internet and find other people with the same database as you, or will find other people running Bitcoin software and ask them for transactions and blocks. And you can send whatever you want to me. I'm going to verify it. And if it's valid, then I'll update my database and I will eventually get to the chain with the most proof of work. That is the goal. This is the thing that Bitcoin developers are working on every day. How do we get this computer program to find the blockchain with the most accumulated proof of work, no matter what the circumstances are, no matter what kind of attacks? Okay, I think that's the... Glad everybody is appreciating it. Thank you so much, and you're welcome. I'm not seeing any more questions. Cool. Okay. Thanks, everybody. Good luck. Good luck learning about Bitcoin. It's the most exciting thing that exists.
Thanks, Matthew. This was great.
All right.